thank Peter and Jonathan very much for the invitation to speak. This is joint work with Nanko Ho, Paul Seelig, and Eugene Xia. And rough outline of what we will be discussing. I would very much appreciate if people ask me questions. So general background, let's let sigma be a compact two-dimensional orientable manifold genus 2. In other words, a double torus. If we puncture the surface or remove a small disk from it, fundamental group is the free group on 4 generators. And we'll consider representations of this fundamental group into the compact group SU2. In particular, we'll study the space where the product of commutators, I need to get used to using the laser pointer. Product of commutators is sent to minus the identity matrix. It looks like this. Fundamental group, as I said before, is free group on 4 generators. So this is often introduced because if you looked at the fundamental group for the closed surface, where you had one relation which says that the product of commutators is equal to the identity, then the representation space, this quotiented by conjugation, is not a smooth manifold. There are singular points. And so instead we consider the space of conjugacy classes of representations that send the product of commutators to minus the identity, and then quotient that by conjugation. And this space is actually a smooth manifold. And this was, let me go back. This was studied by Desala and Ramanan, and they identified it with the space of planes in the intersection of 2 quadrics in a Grassmannian. So this space has been studied quite a lot.
Lisa,
yes?
just a very quick question. So this G4, you're thinking of that as a quasi-Hamiltonian?
No, actually,
space,
no. This I actually am not using. I'm not using the fact. You're quite right that the product of commutators is the group-valued moment map. If you were thinking in the language of Alexeyev, Malkin, Meinrenken, I am. That actually is the group-valued moment map. I'm not really using that property. I'm just using the fact that well, it is implicit in that this space is a level set of the group valued moment map.
Right.
I'm not really using any properties of the group valued moment map.
Okay.
But yes, you're quite right. That is how that enters into Alexeyev, Malkin, Meinrenken's work.
Okay, thank you.
So the quotient space is a special case of the space of gauge equivalence classes of flat SUN connections on a punctured oriented 2 manifold, where you specify that the loops around the punctures get sent to generators of the center of the group. And this space was studied by ATIYAH and Bott in their 1983 paper, The Yang-Mills Equations on Riemann symmetry. Using Morse theory, ATIYAH and Bott found that these spaces were torsion-free and computed their Betti numbers. The ring structure, in the case of SU2, G equals SU2, the ring structure was discovered by Michael Thaddeus using methods from mathematical physics. We will talk a little bit about that, use the Verlinde formula. And in our special case where we're using SU2 and genus 2, remember Thaddeus studied SU2 and arbitrary genus, well, genus 2 and higher. ATIYAH and Bott studied SUN and genus 2 and higher. In the case of SU2 and genus 2, we are able to recover ATIYAH and Bott's result and also Thaddeus's result by much simpler methods. Our main tool is the Meyer-Viator sequence. So the results that we obtain that are actually new, that are not ATIYAH and Bott or Thaddeus or other people, we do have a way of describing a cell decomposition and the ring structure of the space of commuting elements on SU2. This space was previously studied by myself together with Tom Baird and Paul Seelig, and some results previously were obtained by Alejandro Adem and Fred Cohen. They knew the group structure, and in this paper we were able to establish some results on the suspension of this space, which would follow from the results that I will talk about later. Another thing that we are able to obtain is results about the cohomology groups of the 9 manifold, which is the space of representations of the fundamental group before conjugation, and results about the quotient of this manifold where you collapse the subset of elements where at least one of the elements is in the center of SU2, so it's plus or minus the identity. And we obtain a new computation of the cohomology ring of the space of conjugacy classes of representations. But this was the result that was understood previously for all genera by ATIYAH and Bott for groups and Thaddeus for ring structure. We also, I talked about, there is a bundle, M is a bundle over A, because the conjugation action of SU2, actually SU2 quotiented by its center on M is free, so you get a bundle. And we're able to obtain a description of the transition functions of this bundle. Okay. So I'll describe the space of commuting elements. This is a subspace of SU2 cross SU2. This is the set of elements which commute with each other. So you would know some elements in this. So if you have two elements, neither of which is in the center, then they are uniquely conjugate to elements in the maximal torus. So you do have T cross T in there, and then what is left of the conjugation action? What's left is the action of the Weyl group. So you do have basically T cross T quotiented by the Weyl group. That's not everything, because what about the groups, what about the elements in G cross G that were in the center? You have, well, if one of these elements is in the center, then it doesn't matter what the other element is. So you have the center cross G and G cross the center. Those fit together. And of course, you have to talk about what's left of conjugation on that. So that's basically what this space is. And its cohomology as a group was studied by Adem and Cohen, identified by Adem and Cohen in 2006. A cell decomposition of this space was worked out by myself together with Tom Baird and Paul Selig, and also by Michael Crabb. So we will talk about cell decomposition and ring structure of the cohomology. We'll write elements of SU2 always as quaternions. So Z and W are complex numbers. Norm squared of Z plus norm squared of W is equal to 1, so that the determinant of this 2 by 2 matrix is equal to 1. We identified that with a quaternion, Z plus WJ. J is the quaternion, so that J squared is equal to minus 1. And that has the same multiplication as the 2 by 2 matrices, and is somewhat simpler to write. So I will be using that language. Let's let T be the maximal torus of G. In the language of quaternions, this is just the circle group U1. In other words, going back to our 2 by 2 matrix, I mean that Z is equal to I theta and Z bar is equal to minus I theta. W is 0. That's a choice of maximal torus. For G and SU2, there is one element theta between 0 and pi, so that G is conjugate to e to the I theta. This occurs if and only if the trace of G is e to the I theta plus e to the minus I theta, as you would see from this matrix, so 2 cosine theta. SU2 is foliated by its conjugacy classes, which are parameterized by the value of this trace map. So G cross G is foliated by the values of the trace of the commutator map. G cross, I'll write these as W sub theta. So these are elements so that the commutator is conjugate to e to the I theta, or trace of the commutator is equal to 2 cosine theta. I will also define X sub theta, which is the set of matrices G and H where their commutator is actually equal to e to the I theta. I don't think I actually need to define Y sub theta, so I won't bother with that. Eckhart-Meinreinken proved that X sub theta is in fact identified with SO3. I will call this boldface H. SO3 is the same thing as RP3, of course. basically the argument, Eckhart's argument for this was just to show that for regular values of the commutator map, the diffeomorphism type doesn't change, and so he picked a particularly convenient one, which was the one that corresponded to theta equals pi over 2. And there it's possible to write down explicitly, to explicitly identify it with SO3 or RP3. This argument, however, it gives a homeomorphism to SO3. It doesn't actually give it an equivariant homomorphism, equivariant with respect to the nectar clause. So that is one thing that we did in our paper. There is a T equivariant, we established that there is a T equivariant homeomorphism from X theta to SO3. Here, Tx on X theta by conjugation of the G and H, diagonal conjugation, and it acts on SO3 by left translation. And we will need to use the fact that this homeomorphism is equivariant. I'll say something about retractions. So this space of commuting elements, commuting pairs, write that as X sub 0, where the theta is in fact equal to 0. X sub, introduce a notation where intervals mean, so this notation will apply to the X sub open interval, X of the closed interval means the union of all the X thetas. And I will use this notation frequently, where X sub open interval or closed interval or half open, half closed interval means the union of all the thetas in the appropriate interval. So this notation will apply also to the W sub thetas. So I claim here that there's a deformation retraction. We proved that there's a deformation retraction from X of half open interval, where we have omitted only pi, to the space of commuting elements X0. This follows from a theorem that is stated in Milner's book on Morse theory. Milner writes that if you have a smooth manifold M together with a smooth map F from M to R, and if you have C, which is an isolated critical value, and there are no critical values of F between C and another value D, larger value D, then the preimage of the half open interval retracts onto the level set of C. That's really what we're using. We applied this theorem to the trace from X theta to the real numbers. We're really using the gradient flow for the trace function, the trace of the commutator map. So we find that the flow lines for the gradient of the trace are closed. And every point in your x theta is the endpoint of a flow line starting in some x sub u for some non-zero value of u, positive value of u. But we're not able to get a closed form solution for the equation for the flow lines. We did find a different retraction which is explicit, which we can write by studying the arc length of trajectories of the flow. I'll say something about the space of commuting pairs. So with Tom Baird and Paul Selig, we gave the cohomology of the suspension of the space of commuting pairs, showing that it is equivalent to the suspension of a wedge of a collection of spaces. So here we're able to look at W sub 0, 0 pi means all of SU2 cross SU2. And so it decomposes according to the ones where the theta is less than pi and the ones where the theta is bigger than 0, which includes pi. So one of these spaces is homotopy equivalent to the space of commuting pairs. The other space is homotopy equivalent to RP3. And their intersection is just an interval crossed with RP3 crossed with S2. By Meyer-Vietoris, we're able to compute the cohomology of the space of commuting pairs as a ring. Turns out that all cup products are equal to 0. This space was studied by Trevor Bazet in his 2016 PhD thesis at U of T. So our result eventually is that this space is in fact homotopy equivalent to this wedge product. Previously, we had only established that the suspension of the two spaces, the suspensions were equivalent. I'll say something about the cohomology groups. The cohomology groups were identified by Trevor Bazet. Do I want this to be red? No. Z in dimensions 0 and 2, Z plus Z dimension 3, and Z2 dimension. This was Does that seem right? But we proved that the products are zero. Are there questions to this point?
Lisa, so the variety you're calling I, right? That's the pre-image of the identity mod simultaneous conjugation, right?
This thing is just the H, where T commutes with H.
Okay.
So it's not.
So it includes, of course, T cross T quotiented by duality. Yeah, always quotiented by conjugation.
Right. So and so as you I think mentioned earlier, you can identify this space with T times T mod the Weyl group.
Not only, because that description only applies if that description only applies when both G and H are in a unique maximal torus. That description doesn't apply for the case where at least one of G and H is in the center.
I see. You're only getting, I see. Okay. I was just going to ask why it doesn't reduce to T times T mod W, in which case, but no, it's right. Okay. Thank you.
That's all. You have to deal with the points where G is in the center and or H is in the center. Okay. I'll go on. So M, as before, is the set of points where the product of commutators is minus the identity. And this one actually is a manifold. We defined its quotient by conjugation by G. The center, the center acts trivially, so you have a free action of SO3. So this is a principal SO3 bundle. Oh.
Lisa, were you meaning to write on the screen?
No, okay, no, there's.
You have to change the page.
Yeah, I know. I'm trying to figure out
Or to go to the next page.
I had done that, except it didn't. Okay. I need to figure out why it didn't. I can't see that the page is not moving from one to another. I evidently have to.
Stop sharing and share again.
Yeah, okay. Okay. Okay, that's better. Thanks. Sorry about that.
No,
Okay.
that's fine.
Yeah, sorry
Thanks.
about that. Okay. So, yeah, M is universe minus what? Minus I. A 9 manifold. And then there's its quotient by G. And this A, which is the quotient. So you have a principal. M is a principal bundle over A with fiber SO3. And Newstead had found in this case, and later ATIYAH and Bott more generally, the cohomology groups of A with integer coefficients are Z for dimensions 2, 4, 0, 6, 2, and 4, and Z4 for dimension 3. Space is simply connected, nothing for dimension 1 and nothing for dimension 5. Satisfies planetary duality. So we'll see how we recover that. Newstead found the generators for all G. ATIYAH and Bott found them for G equals SUN, for all N and all G. G greater than or equal to 2. So let me define A sub theta, which is 4 tuples where the bracket of product of commutators is minus the identity. We insist that the commutator of X and Y is conjugate to ATIYAH theta. That means that correspondingly the commutator of X prime, Y prime is equal to ATIYAH of pi minus theta. So we see that A sub 0 is W, the notation W was introduced for things where tuples G and H where commutator of G and H was equal to the identity. And this one would be where the commutators of G and H is equal to minus the identity. So both of these are equal to the space of commuting elements, A sub 0 and A sub pi. For theta between 0 and pi, you have that A sub theta is equal to the quotient of W theta cross W pi minus theta, quotiented by conjugation. Then we can restrict to W theta meant that you knew what the conjugacy class of the commutator was. X sub theta means that you have restricted the value of the commutator, not just its conjugacy class. So here, when you've made that restriction, you can quotient only by the maximal torus. So because we had, using Meinrinken's result, we'd established that X sub theta was equal to RP3. So these things are just RP3 cross RP3, quotiented by the maximal torus. In other words, RP3 plus S2. S2 is RP3 quotient by 2. We still have that A with the open interval is homotopy equivalent to the space of commuting elements. And as I said before, we're able to write an explicit retraction for this. So this means that the space A is one copy of, in fact, two copies of the space of commuting elements quotiented by these are really the x of a of the open interval, and this would be a of the other open interval, and then you're amalgamating over the interior, the points where theta is between 0 and pi. So think of this as amalgamated product. So that gives a characterization of A, and Meyer-Gay-Torres gives the really Meyer-Gay-Torres. You're thinking of this as this is your, this could be your U, and this could be your V, and this thing can be your U-intercept V. So that's the Meyer-Gay-Torres, and Meyer-Gay-Torres gives the cohomology groups as I outlined. Meyer-Gay-Torres using this decomposition. Any questions to this point? If not, I'll back up to some of what was known previously. Let me just go over the distinction between intersection pairings and generators and relations. Homology ring of the space A, as we discussed, is generated by a two class, which you can think of as the Durand cohomology class of the symplectic form. This space is a symplectic manifold. And another four-dimensional class, which I'll call A. And there are three generators of degree 3. Use that notation. So if you want to understand the cohomology as a ring, you need to understand the relations. In other words, the polynomials in these generators which take the value 0. But because the cohomology satisfies Poincare duality, understanding the relations is the same thing as understanding the intersection pairings. In other words, understanding the values of polynomials in the generators when they are evaluated on the fundamental class. That encodes the same information as the relations. Through Durand cohomology, you can think of these cohomology classes as closed differential forms, and you can think of the operation of evaluating on the fundamental class as just integrating these closed differential forms. So, sorry, I changed my notation, and I'm a newbie with the iPad, and so I was too lazy to go back and rewrite the slide instead of just writing on it with good notes. So all I wanted to do here was change the notation to something that was a bit more logical. So here we're talking, I'm identifying 6-dimensional cohomology classes, which are products of, we had these 4 generators, B1, B2, B1 prime, B2 prime. So there are, I've chosen 2 of those, called those gamma and gamma prime. So I wrote the gammas are the ones that are products of classes that don't have primes, and gamma prime is product of B1 prime and B2 prime. And all the other classes are all the other choices of products give you 0. This, the four generators, 2 ways of choose 2 of them to make a product. So there are 4 choose 2 is 6. So these ones are the only ones that give you something non-zero. These ones give you 0. One relation that was found by Michael Thaddeus is that, let me introduce, I'll call A sub G is, we've only been talking about something that I called A, which was for genus 2. Suppose you do the same thing for genus G. So you still have classes which are representations of the fundamental group on a surface which is a genus G surface with 1 boundary component, and the loops around the boundary is required to go to minus the identity. So we do the same thing for genus G. So our space A becomes A sub 2 in this notation. So the relation that Michael Thaddeus found is that if you have some class in the A's and F's, doesn't matter, in fact, whether you use gamma or gamma prime, this is the same thing as taking the integral over A sub G of the same class over A sub G minus 1, which is, let me remind you the dimension A sub G is 6G minus 6. So point is that the dimension of A sub G minus 1 is 6 less than the dimension of A sub G. And in fact, it's possible to find a codimension 6 submanifold of A sub G, which is isomorphic to, possible to find an A sub G codimension 6 submanifold of A sub G, which is isomorphic to A sub G minus 1. So all we're saying is you integrate your classes over that submanifold of codimension 6. And that gives you the same thing as integrating over A sub G with the gamma in. So what this means is that the gamma and gamma prime are Poincare dual to this codimension 6 submanifold. Okay, we will be using this. So let me in fact define big gamma, which is the sum of 2 times little gamma plus gamma prime. And in our case, our A has dimension 6, and the space corresponding to genus 1 is just a collection of points. So our relation becomes that the integral over A of the big gamma is 4. This, in fact, is equivalent to that the integral of the little gamma either of the little gammas gives you 1. There's a symmetry argument that tells you that this integral with the gamma and the integral with the gamma prime, those have to be equal. This example is discussed in a survey article, which is written by me together with Aidan Lindberg and Steve Ryan. Also on archive. Any questions to this point? Okay, I'll talk about the Verlinde formula. Verlinde formula tells you about the dimension of the space of holomorphic sections of powers of the pre-quantum line bundle. Pre-quantum line bundle is a line bundle with a connection whose curvature is the symplectic form. So that means that C1 of this line bundle is in fact the symplectic form, which is our F in terms of the generator. So yeah, in fact, what I've written down is in fact just the Riemann-Roch. This is just Riemann-Roch or Grothendieck Riemann-Roch. Says that, well, together with, you need some assumption that says that the higher cohomology classes are equal to 0. So that this really is the Euler characteristic of this object. So this is given by the Chern character of the kth power of the line bundle and, oops, and the Todd class of A. So in terms of our previous generators, the first Chern class of the pre-quantum line bundle is our class F, which is the de Rham cohomology class of the symplectic form. And so the Chern character is exponential of F. The Todd genus of A, the Todd class of A, is exponential of F multiplied by a polynomial in the class A. So this polynomial is written in terms of square root of A, but remember that both the numerator and denominator of this function are odd functions of the variable square root of A, so their quotient is an even function, so it's in fact a polynomial in A. And actually, if you write out the Taylor series of this function, you will note that the first term in the first term in the Taylor series of the numerator and the denominator are both, well, they would both be in this variable, so fine. Higher order. So you wind up with 1 plus higher order. So you can in fact invert the series. So you do actually get, well, you get an infinite series in A, but because we're in finite dimensions, you discard all the terms that are dimension higher than the dimension of the manifold. So that's okay. This really is a polynomial in A, not in square root of A. Okay, the result turns out to be something proved by a number of different groups around the same time. Bovil, Laszlo, Faltings, Kumar, Narasimhan, Ramanathan, Sagie, and Tsuchiya Ueno Yamada. They established this formula for the dimension of the space of holomorphic sections for SUN connections on a surface of genus G. There have been many generalizations to groups other than SUN, and things like parabolic bundles and a lot of other results. Anyway, for our case, I've written this for genus G and for SU2 connections. This is a sum from M equals 1 to K plus 1. This formula can be used to extract formulas for the intersection pairings of the classes A and F. And that is what Michael Thaddeus did. So this formula is due to Michael Thaddeus using the Verlinde formula. This is in terms of, so this is written for general, for SU2, general genus G greater than or equal to 2, and the BJs are Bernoulli numbers. So here I've written the special case G equals 2. The general case, general G, is due to Thaddeus. Restricting to G equals 2, you get this formula. And we need M and N to be greater than or equal to 0, and to add to the dimension of the manifold. So the only relevant values are, only relevant values are N equals 0 and N equals 1. So what you extract in this case is that the integral of A cubed is equal to 4. This is this symplectic volume. And N equals 1, you extract that the integral of A times F is also equal to 4. So we see that A times F is equal to the fundamental class, and F squared is equal to 4 times A. And these can be extracted from Thaddeus's formula from the previous section. So that's resume of what was known about that particular case. So let me go on to discuss the 9 manifold. So M, remember, is mu inverse of minus the identity. And we write this as a sum over the M thetas, which are, M theta is where the commutator of x and y is conjugate to e to the I theta. So we see that, possible to see that if you restrict the value of theta to not be equal to pi, then in fact, the bundle m over a is a trivial bundle. So we just need to study the trivialization over subsets where theta is less than pi and where theta is bigger than 0. So you get a transition function for their intersection, which is where theta is between 0 and pi, not equal to 0 or pi. And the transition function turns out just to be, so we're thinking of this as a subset of G cross G. So the transition function is just the map that sends G comma H to G inverse H. Let me introduce M caret, which means M quotiented by the subset where some of the elements are in the center of the group, plus or minus the other. Turns out that the cohomology groups of M caret with mod 2 coefficients are Z2 in all dimensions other than 1 and 8 and 0 in those dimensions. And cohomology groups of this space with integer coefficients are Z for dimensions 0, 2, 7, and 9, Z4 for 2 equals 4 and 6 and 0 otherwise. I would like to mention an old theorem of CTC Wall, which states that if you have a 6-manifold where all the cohomology groups are Z for dimensions 0, 4, 0, 2, 4, and 6, and for dimension 3, you have, or degree 3, you have direct sum of even number of copies of Z. So in this case, in fact, this is what you would get if you had, if your manifold were a connected sum with a collection of copies of S3 cross S3, with a manifold that didn't have anything in degree 3. And Wall's theorem asserts that, in fact, such a manifold Y prime does exist, provided that the cohomology is of this form. So it's just interesting to observe that our manifold is of this form. We can write A is equal to, we'll write A caret connected sum with 2 copies of S3 cross S3. And our A caret is space where you take the quotient of A by the subset where some of the elements are, at least one of the elements is of degree, is in the center of the group. It's just interesting that our cohomology did did come out to be exactly of that form. It's not clear that, it's not clear from anything that we did that there is an A caret which is a manifold. This quotient construction does not produce, if you start with A is a smooth manifold and A sub u is a subset, that does not produce a smooth manifold. So it's interesting to see how that conforms with Wall's theorem. So I'll stop there.